Let's do a sound check. Alright. Let's do a sound check. Alright, cool, sound works. Thank you everyone. Welcome to this weekend's series Falcon streams. So last time we implemented a lot of cool things. We now have a 3D scene. We now are using draw indirect, so basically there's a single draw call on the CPU side that just draws everything that we have. Let's see what we have right now. Let's check that it works. We we can render a lot of kittens. So right now this scene looks slightly not uninteresting necessarily, but like it's not obvious that we are doing draw indirect because you could achieve the same effect with instanced rendering. But we will switch to we will switch to drawing different kinds of meshes today. And we will start doing GPU side culling. I don't know how far we can get today, but there's also tomorrow. So basically the goal is, hey, let's render multiple meshes, let's do GPU side culling per object for now, not per cluster. We are already doing backface culling per cluster, but other types of culling per cluster might come later. And then but start doing level of detail. Right now the problem is we are kind of peaking in terms of the number of objects that we can render, because the more objects you add, the more triangles you have, right? And these faraway objects don't really need the same number of triangles, but they use that anyway. So we'll have to fix that. And I doubt we'll really have time for much else this weekend. Definitely not today, but in general I want to also start exploring occlusion culling. But that might need to wait up until at some point later, because also we might wanna do like camera movement and something. I don't know. We'll see how it goes. So let us start from the beginning. But actually, let's do a tiny bit of cleanup first, because I think we left things off last time in a pretty good spot. To move some of the code out of this CPP file. Let's see how much code that would be. Not that much. We can move like a few hundred lines out of this CPP file, which seems worthwhile. So I basically want to move device initialization out, and then swapchain out in something separate, probably. Yeah, we can move swapchain into a separate file, and the buffer image helpers into a separate file. So let's quickly do that. Let me make sure that I don't have. We won't be profiling things too much today. We will be implementing culling, so like we will look at performance, but we won't be doing that rigorously. Like we'll still run with vsync off, on, and stuff like that. Okay, yeah, so we don't have any changes. So let's just quickly move things around so that our main file is slightly easier to work with. So let's see. So I want basically a file for swapchain. We tried to do the swapchain stuff very briefly on some stream before. It didn't quite work out, but there was a problem where the swapchain was sort of tightly coupled to the actual rendering of the scene, because we were rendering directly into the swapchain buffers. We're not doing that anymore, so things should be easier for us. So swapchain, and then I want device. And I want, let's call that resources or something. We have a bit of helpers for buffers and images, and let's just call them resources. because they share a bit of code. I think that might be useful. Okay. Yeah, now let's just move stuff. So let's move device first. Let's see. Create instance, debug callback, graphics family index, all of the device selection and device creation, so that we don't need here. Or I guess I should have, yeah. So that goes to the swapchain source file. And then I forget what we are doing for the various. Okay, yes, we have common include file basically. Okay. And oh wait, this was not swapchain, this was device. Okay. Oh, why did it add pragma once here? Interesting. Okay. Visual Studio added pragma once to CVB file. That's odd. Oh, maybe I created it as a header file. Alright. So then swapchain code. So yeah, all of that. We will probably leave the semaphore stuff for now. This is a good way to, whenever you come back to the code that you haven't worked on for a while, if you have something that you remember that's sort of you wanted to do and it didn't seem hard, so you didn't do it, it is generally not a bad idea to start from that, because it kind of gets you back in the flow. And it makes it easier to sort of, yeah, to get back basically into whatever you were writing, and then you can start actually solving more complex problems. And that can go better. Oh, right, and then we have the vsync defined that I guess we'll move here. Alright, and finally we have the resource stuff. For now, I only want to move. Where is this even? Aha, yeah, this stuff. So we had like a buffer struct and an image struct. So let's. Oh, and we had some upload helpers. Yeah, this can all go here. And then images, and then obviously we'll have to like fish out the declarations of all of the functions that work on these objects. But yeah, this should significantly clean up the code. So that goes here, I guess. It can be static. It can be static. That all needs to be exposed. And we could move the barrier thing. Yeah, all of this, all of the rest, I think for now is good to stay where it is. So now we have a bit less sort of helper, not helpers, like a bit less code basically, which is good. So then we'll have to include all of that. It's also sort of good for build time in general, but it's not like our build times were bad. We just want to clean stuff up. I don't know why I sorted them like this. Let me just sort them by alphabet. So, okay. And now we need to actually make this compile, right? Which means that we'll need to figure out which functions we were using, such as create instance, right? And then expose them as yeah, as like functions in the header. So create instance. Is there like vertical splitting in Visual Studio or some splitting? Okay. No. Can I like open another file here? Okay. You know what? Forget it. Let's just, so this should be static. Well, yeah. Alright, whatever. I think we use that externally. I think this is just device helper stuff. So that, we need that. Alright. Oh, this one is interesting. Are we? Oh yeah, right. We are querying this support with this code. That's fine. For now, this can stay. In theory, we could extract this into a separate function, but we won't bother for now. And then let's do the same for swapchain. I think this is also a public function. I think this is an internal function. Yeah, so I think this one is a public function. And then that. This one is slightly weird because we stopped doing things like that. So maybe let's not do things like that. Although, oh right, this function used to have more than one line. Okay, that's fine. Let's keep that. And then we have resize. Okay, so there's that. Right, algorithm. GLW window is undefined. Wait, what? Oh, no, wait, hold on. Oh, I see, okay. Yeah, we need to forward declare this essentially. Okay, yeah, now we need to move the resource functions out. Or not out, like declare. Oh, we are doing barrier. Yeah, okay, we'll need to move the barrier stuff here as well, which is just as well. This upload function is technically not very reusable. Like we'll have to. I'm not even sure I want to have this here. Maybe for now I should. Yeah, maybe. Let's keep this in this file, but this function is kind of short-sighted, like we will have to rework this function for sure. It is not optimal. It creates like a command buffer for each, allocates command buffer for each upload, uploads one buffer in one go, which means that there is like a lot of barriers that are excessive, so basically it's not really good for performance, but it's more convenient. But for now we'll just keep this in that file, so that's fine. Yeah, I guess I will just move this barrier help us as well, which seems okay. Right. Oh, did I kill the... Yeah, I should not have done that. Okay. So that was nice and easy. We still work. And now there's like a lot of code that was deleted from the main source file, right? So that's nice. So let's just commit that. Day 11. Move some code out of. Alright, so now that we've done that, I'm a bit back in the flow, and now I can start doing. So the next thing I want to do is I want to start rendering multiple types of meshes, and after this we will start doing culling. So right now we'll just render kittens. I'm not actually sure where they came. Can I like use them on stream? I don't know where the meshes that I have are from, but I think this is just from most of the meshes that I have. They're like, at some point I went to Sketchfab and just like looked at a bunch of meshes that were free for download. They might not be free for use, like there's probably a license associated with redistributing them, but I'm not uploading this to my repository, so it's probably fine. So yeah, there's like a few meshes that are also the same scale, roughly speaking, as a kitten, and they're basically, I think, several sculptures sort of made out of clay. This is like clay crazy. There's also clay drunk. And there's also some other thing. Clay panic. So, you know, we can try to, instead of drawing one kind of mesh, we'll randomly draw one of the, I guess, 3 or 4 meshes, right? So to do that, we obviously have to load different meshes, but the more important part is that we will have to add some data somewhere. I'm trying to figure out. Actually, do we? Maybe it will. For now, maybe it will kind of work out because the meshlet count. Yeah, we don't really need actually any extra data because we are filling all of the buffer, all of the like draw commands right now offline somewhere. I'm not sure where. Yeah, here. So don't even need anything complicated here. Which I guess is good. One thing I wanted is I wanted to stop. One other thing I wanted is I wanted to stop rounding the meshlet size up. But for now we will not do that. So yeah, let me think. I guess here I can use, there's this thing called first task. Let me think. So then there will be the buffer here somewhere. Oh. How did that happen? Okay. I don't know how that happened. Okay. So this will be fine, right? So basically the only thing is the meshlet index has to be computed with an offset. But then if I use first task, yeah, so I think what I want to start doing is I want to start adding a bit of information to the draw code structure, so that in the shaders we can address. So far the assumption has been that all of these buffers, so there's like a buffer with the meshlet headers, which is just how many vertices each meshlet has, etc. There's a buffer with the data for indices and stuff, and then there's a buffer with the vertices. So far the assumption has been that there's only a single mesh everywhere, like there's only a single mesh stored in all of these arrays, right? And we need to start drawing more than one, so we'll need to have some offsets into these. I actually said on stream, like on the second day or something, that we will be using one giant buffer, and it will become apparent why way later in the stream. So that's kind of the point where we will just have multiple meshes that we are all uploading to all of these different buffers, and then we will set up both traditional pipeline and the mesh shading pipeline to reference the correct segments of these buffers when we draw stuff. So that is the plan. Let's start doing that. So yeah, the first thing I kind of want to do is I want to kill this. So right now we are aligning the number of meshlets that we use up to a 32 meshlet boundary. And the reason why we do this is we have 32, like a warp of 32 threads processing each group of meshlets. So if we don't round, and then we are like dividing the size by 32 somewhere. So if you don't round, we'll have a missing, yeah, so see there's like a hole in the kitten. So that's not great, because we are not rendering some of the stuff. So to fix that, we need to store the actual size of the meshlets. Well, so the first thing that we need is we need to round the number of tasks up when dividing by 32. But then that can, like if we just do this right now, bad things might happen. Let's just do that right now and see bad things happen, because that'll be fun. Yeah, so right, if you have like one mesh, let's say, then you still want one invocation, one warp with like task shader threads. So this really has to be like plus 31 or 32, which rounds it up. Well, we don't see anything crazy happening, but we are in like undefined behavior territory because we are accessing meshlet data outside of the bounds, which is not good. So to fix that, in the task shader, we will need to change this code. Effectively, we'll need to change this code so that we are never going past the bounds of the array, right? So when we call, we can just say that, well, so there will be the last warp. Let me think. Yeah, assuming that the buffer is actually padded, I think we should just be able to do some check here, something along the lines of, if this is the last meshlet group, which is basically if let's see, so I think it should be something like, oh, not hold on, if like MGI times 32 plus 32 is greater than or equal than the meshlet count, which we'll have to store, then we'll have to clamp the count by the difference. Then it's like count is max, I mean min, count meshlet count, basically the delta. No, not the delta, hold on. Damn it. Meshlet count minus MGI times 32. So I guess the other way to phrase this is, but yeah, anyway, so I think this is correct, maybe. But then we'll have to do the same thing in this shader. So to do that, we need a meshlet count, and this is just as well because we will actually need this stuff in the future. So let's add this here for now, and in the shader. And we'll use it for more than just this, but it's good that we'll add this like now. So let me look at the math again. this is the uniform. Well, basically, right, I can do this here. I mean, I guess I can do this here as well. Oh yeah, but yeah, I want to do this like this, probably. And then I don't think I need this if necessarily. Yeah. So this should be just actually very simple. Basically what I'm saying is the last warp that processes tasks, if you have like one mesh, let's say, right, then we still spawn one task, but then the task may read the data of more than one meshlets, but I don't really care about this for now because let's just assume we pad the buffer to the correct size. I just don't want, like, when we start rendering multiple meshes, I don't want... Maybe I should have waited up until then because the problem would have become more obvious. But like, whatever. I don't want, when we have multiple meshes, there will be meshlet data of one mesh, and then immediately after this there will be meshlet data of another mesh. And I just don't want the first mesh to just read like overflow data from the next one and just render these triangles but in like the wrong place. And so what we are saying here is that let's say we have computed that for this work there's like three, let's say there's total 5 meshlets, and then let's say there's 3 visible, but only the first 3... No, damn it, this doesn't work like this. Okay, no, yeah, I have to... Alright, I have to do this earlier in the pipeline, because if I called some of them, then I don't know what the correct count is. So I have to integrate this here, really. Basically, it should be something like... Alright, I didn't really want to do this like this, but it's fine. Like, if the index is less than the... if the index is greater than or equal than the count, then we should not accept the mesh. But here I need to do the thing that I was talking about earlier, I guess, which is that we'll actually do the meshlet count minus something, mg items 32, which is equivalent to mi actually in this case, so yeah. Alright, yeah, I think this will work. Let's just... oh. What? Okay. Does this work like this? And nothing is rendering. Does this work like this? Interesting. I see, so I guess there's no bitwise. Okay, whatever. Oh, we are not filling the meshlet count now, so nothing is rendering. So that's fine. All right. So I think it will be hard to know if these sort of guards work, but I think they might, and we'll be able to test this when we add the second mesh. So note, we assume that it's safe to read meshlet data out of bounds. We'll just get data from the next mesh, or there will be some overflow after, like our buffer is 128 megs, so I guess it's aligned. We should make sure that after the final mesh we add a bit of padding so that we don't have to deal with that. The other way, maybe the more correct way, is to just wrap this entire thing with an if. But I don't want to do this right now because it interacts in interesting ways with this like subgroup ballot stuff. And maybe it'll all work fine, but maybe not. I just don't want to mess with this for now. It should not be that hard to fix. I just don't want to do that. because I'll have to like move the boolean out. Or actually, is this just, maybe this is just this. Maybe this is not that hard. So maybe we just need to say this. And then just do that. And then the rest stays. Maybe this is nicer actually. Alright, let's assume this works. I'm slightly unclear about the implications of the conditional here, but maybe it's fine because this is outside of the conditional flow. So let's assume this is fine, and then we can add the second mesh and see how it goes. So yeah, so the next thing is I want a second mesh. To do that, I kind of want to add the meshlet offset here so that I can index data correctly everywhere where I'm reading meshlets. So let's just go ahead and add this now first. And then I think everything else I'm okay with. I think everything else will work as is for now. We might not be doing things super optimally right now, because what I want to do is I want to store all of the indices that we are storing to the vertex buffer in various like meshlet structures and stuff. They're 32-bit, and you can't really have more than like 4 billion vertices, because that's, what is it? Our vertex is like 20 bytes or whatever it was, so that's like 80 gigabytes of memory. I don't have 80 gigabytes of memory, so for now we'll just do that and store indices that are just like, there's a giant vertex buffer, and let's say there's like many meshes and they add up to like 10 million vertices, and we'll just store indices from 0 to 10 million. At some point we might want to start using 16-bit indices, but for now this is not a priority, so let's just keep things simple. So for now this is just like 0, but then I want to add this to some places. Let's see. I don't really need to touch that. I basically only need to be super careful with this task shader, but I don't need to touch anything else really. Yeah, I kind of want to add like MIO or something, meshlet index with an offset. Oh, come on. Damn it. I'm starting to want to uninstall this GLSL extension because it's hurting me more than it's helping me. Because it's really painful to edit shaders. But I'll lose syntax. Let me do that. I'd rather, I guess, lose syntax highlighting than have a really bad time typing. So I can disable this extension, and then I'll have to restart Visual Studio for that. I meant to file a bug on this, but I forgot. I'm not sure where the bug is, but like 2 extensions that I'm using are interacting really poorly. Yeah, so now it's good. Okay. Yeah, so that, and then whenever we use MI for indexing, we need to be using MIO. But then this stuff still uses MI. So the other way to do this is I don't need a second index, because I can be I can do that, and then here I just need to compare versus mesh draw meshlet offset plus, which is slightly redundant, but it's not too bad. Yeah, I think this is right. Alright, so now we are ready to load multiple meshes. So what we'll do probably is just, you pass multiple command line arguments and we'll just load all of them. So that it will be like mesh list. Let's see. So this structure becomes a bit of a, like, it's not really a mesh anymore. But we will need a structure called mesh. So let's rename this to, let's say, geometry. And let's add a structure called mesh, which will just contain the offsets and these, like, basically the information about the mesh that we have loaded. So we need meshlet offset meshlet count. And we also need index offset index count for the traditional rasterization pipeline. Index. And then everything else, I think, will just, everything else is fine. And then we'll do this, right? And then so load mesh will basically add data, so to speak, to the, to the buffer. How does this work in terms of code flow? Alright, we call load mesh, and then we call this thing okay. But then there's the vertex count here. Need to use. Okay, so I think we will merge these two functions because this will make things a bit easier for us. Like build meshlets. So then the function will, we can like make an intermediate mesh structure, but I don't think we really need that. I think we're doing okay. So I want to rename this to something like triangle vertices, so that it's less ambiguous, and then we'll just have vector vertex vertices, indices. So just basically when we load the mesh, we will first compute and optimize and like everything all in local vectors, and then we'll build meshlets. So if build meshlets, let's just do that. Turn through here. Right. So then at the end, after we've computed the vertex buffer and the index buffer, we basically need to append. Maybe I should have been using index offsets because then I could just copy. But no, for now we will just so this code will not be very efficient for now, but it's fine. So for each index, we want to push this to the, what do we call this, result? To the sort of global index buffer, but the trick is we need to offset it by the like there's a range in the mesh where the vertices will start, which I guess we can say that it's vertex offset, which is the current size of the, like however many vertices we have accumulated so far. So yeah, so I could just store this and apply this elsewhere, but then I have to move this, like add this to the shaders, which might be nicer. But let's start like this, and then we'll switch this around. And then just push all vertices. This could be more efficient, but for now I don't care. And then we need a meshlet data. So we'll compute the meshlets using the local vectors that we have created. But then, so that could be just this thing. So this, yeah, maybe I should just move the vertex offset to the shader. It's less confusing that way. If this code works, then we will do that next. Okay, I think this is correct. So I'm applying basically vertex offset to the indices that are used for the traditional pipeline, and also to the indices that will be used for the mesh shading pipeline. And I'm not applying any offsets anywhere else, but I don't think I need to. So I think I'm good. Yeah, this could be something like, I guess, this. And like ideally we'd be probably storing this data directly to the buffer that we can be using to upload things to upload from later, like to a scratch buffer, because right now we are keeping these giant vectors for like really no reason at all. They're just going to the GPU. So ideally to do remove these vectors, they are just scratch. It's like a second scratch copy that's just wasting space. So ideally we should reflow this a bit so that we don't have to do that. But for now it's fine. We have a lot of memory on this machine, so we don't care. Yeah, okay, so I think this is good. And then we'll just go through all command line arguments, you know, try to load the mesh. Oh, yeah. And this function does everything for us. I guess we can say say this. This is function. Yeah, okay, good. So now we have more than one mesh if we have more than one argument. So what we will do is for each draw call count, we'll just pick a random mesh. So it will be like random percent. Oh, we didn't fill this. We'll never do. So yeah, after we've loaded the mesh, let's just fill the mesh structure. It just has offsets and counts. Oh, well. Result indices size, and then meshlet offset. Alright, so now when we randomly pick a mesh that we want to draw, or I guess we can be just, yeah, like this, geometry meshes. So let's see. We'll just need to pass everything that we have already computed. So the indirect command should have the offset for the index buffer. First index, I wanna say, yeah, should be first index. So this will be the index offset. Alright, and yeah, the meshlet count is just this. Alright, so I think that's it. I don't think we need to do anything else. I mean, yeah, now we need to change, we've renamed this. And we need to change more stuff. Right. Some of this stuff is now gonna be hard to compute, because not hard to compute necessarily. Triangles per second in general is gonna be hard to compute once we do GPU culling. Like right now it's super easy. We just basically say, hey, like the total, you know, triangle count. Or I guess this actually might overflow. No, I don't think it can overflow, it's fine. And then triangle count that. Right, so right now we are not culling the meshes before we submit them to the GPU. So it's pretty straightforward to just say, hey, just add this up. Wait, yeah, okay. All good. And then let's don't print that anymore, because who cares? And then here we will say triangle count, right? Of course, when we start culling, it becomes unclear what the triangle per second number should be, but we'll see. All right, yay! Now we are crashing. What's going on? Index count, vertex count, vertices. Oh, whoa. Whoa, wait. That. Oh, did we find a bug? Hold on. Yeah, I understand what's happening here, but well, no, maybe I don't. Well, right, yes, we are not calling this function correctly. This is what's happening. We have renamed this to triangle vertices. Alright, okay, so we can still draw kittens. Now let's see, but we are only supplying one mesh. Now let's see if we can actually draw more stuff. Let's just, as an experiment, I forget if Arctic Fox was like the right size. Well, we clearly didn't. We clearly didn't do anything here. Let's see. Our code doesn't work yet. Oh, right. Because we are loading the kitten twice. Okay. Okay. Our code does not work. We can clearly see. I don't think we see any other meshes. I think we see something to the extent of whenever we are trying to draw like another mesh, which is like an Arctic Fox, and I picked that because it has way fewer triangles. I think we are seeing that we are rendering the kitten data, but up to the number of triangles in this mesh. Oh, let's check if actually. Okay. Alright, so we have bugs in our code, so now we'll have to think about this and fix the bugs. Alright, so that's gonna be fun. Let's see. So let me look at this code again, because it's always good to look at the code first. Don't need to do this in this order. So let me look at the non-meshlet stuff first. Right, so we have the vertex offset, and then we push all of the vertices, and then we push all of the indices, and then we offset that. Okay. Okay. Index offset, index counts, so far so good. Is the first index not the right thing to use? I think it should be. Yeah, I think this should be correct. Oh, actually, do we know that it doesn't work? Because maybe in the, in the new pipeline, in the mesh shading pipeline, definitely it doesn't work. But maybe the fox is just too big, so it's hard to see what the hell. Yeah, okay, you know what? Hold on, maybe the meshlet pipeline is not working, but maybe the other thing works. Let me draw kittens. And then I found another mesh that we'll use for now, this guy. It's a bit smaller, but alright, never mind. So the traditional pipeline now works. So you can clearly see that some of these guys are kittens, and some of these are these, like, I'm assuming a demon creature with like horns. Right, the scale doesn't really match just because the scale of the meshes is different, right? So we could draw like this clay guys, which we will do in a second, and that will work, right? But now, so the meshlet, we forgot to do something for the meshlet path, because clearly it's the same thing actually, right? We are drawing like a kitten geometry, which means that we are not offsetting something correctly, which is odd because I thought we are offsetting everything. Oh, but we might not be offsetting the meshlet data in the shader as well. So let me see. Oh no, wait, hold on. Data offset. This seems correct to me. Oh, okay. All right. Okay. Okay. All right. So now we can render multiple meshes. That is good. Let's do clay padding, was it? Right. So that's nice. Now we can clearly see that we are rendering more than just a kitten. Let's add the other. Oh, what? I see. Okay. Crazy drunk. And let's add this demon for change, you know. All right. And now it takes a couple of seconds to start up, I think, because in debug we are doing some inefficient things with vectors. Maybe we should stop using vectors. It's also getting slightly hard to figure out if our code... our code works, but it's not really optimal. Like, it's basically a bit chaotic on screen, right? It's hard to really understand what's going on. But our code does work. Oh, and also we are not... I don't think we are computing the number of triangles correctly or something. Let's see. Oh, great. Okay. Are we dividing this by 3 somewhere? Oh, why are we okay, right, yes. So that is now incorrect. That is now incorrect. Alright, so yeah, we are hovering around 15 billion triangles per second, and this is without vsync, so with vsync it will be more. And we are drawing really varied meshes now, so some of them may not be... I think for these meshes the culling is struggling a bit for these character meshes, because their tessellation is just on the side of... Like, it's hard to do good culling here. Anyway, but this is good enough for now. Alright, so that worked. Let's rename this to, yeah, like draws per sec. Draws. Okay. And I guess we're running in debug. Alright. So yeah, I guess I want to move the vertex offsetting to the shader, because it's slightly awkward to do this here anyway, and I might as well do this in the shader. Let's do that. I don't know if I'll need the count, but it's fine. After this, we can just use the same thing here. It's basically that. And I don't really need to be applying this offset anymore. I will just do this in the shader. Yeah. Not clear if this is a good idea, but like long term we want to switch to 16-bit indices, so I guess it might be a good idea. What I'm not sure about is, so we are doing the, for the non-meshlet path. For the meshlet path we have to do everything ourselves. For the non-meshlet path we are using this thing called GL vertex index, I think. And I forget the semantics there, so I'll need to Google that. Right, so I think this already has the offset. So I think for the non-RTX, for the non-mesh shading path, I need to use that guy. I think, yeah. And for the mesh shading path we have to do everything ourselves. So let's add this data here. Offset. This data is only used for mesh shading pipeline, but it's not like it's fine, we'll just keep it here. it's not that much space. So hopefully it doesn't really affect our performance, because this is just per draw call, it's not like per meshlet or anything like that. And then now it will not work because I'm not doing anything in the shader. Let's check that, right? So like things are really messed up here. Now it's really clear. You can see that meshes pull data from like pull vertex data from other meshes. Yes, the old path works. Now let's just change the mesh shader to just offset that. Should be easy. It's like the wrong vertex offset, okay. So here I have to add mesh draw vertex offset. It did not help. Oh, I'm not feeling this, of course. I never am. Jesus. Okay, cool. So I guess that's it for multiple meshes, right? I don't think we are missing anything. I think we are doing fine. Potentially. Yeah, I think we're good. Okay. So that is good. Let us commit that. So now we have reached a point where it's obvious, hey, you can't really do this with instancing anymore, right? We really needed the draw and direct stuff that we did last time. It's just last time it wasn't obvious why, but this time it's very obvious why, because we are rendering many meshes. Oh yeah, so the other thing is, let's check what would have happened, I guess, if we didn't do the thing that we did without a way to really test that thing. So let's first check what happens when we disable culling. So now let's try to see, and I don't know if this will be visible as bugs, but let's try to see what was it like. Yeah. It is not. I don't see any bugs. That is unfortunate. I was hoping for a demonstration here. Oh well. Okay. What? Maybe our code doesn't. Oh, are we still padding something somewhere? No? I think I removed that. Yeah, I think I removed that. Okay. Alright, what would have happened if we didn't do this here? Same thing. So, okay, I cannot prove to you that the thing that we did here was useful, but I think it was. So let's just leave it at that. Alright, so let's commit that. Day 11, multiple mesh support. We now load all command line, all like obj files pass through command line argument, and randomly distribute them on screen. Yay. And that worked with few bugs on our side. What's our frame time, by the way? It's like 5 milliseconds. What's the frame time here? In release mode. It's also like 6, yeah, okay. Alright. Okay, so that's all good and well. The number of triangles is now unreadable because it represents this sum total of all triangles per frame. So let us draw the floating point value. Okay, yeah, so we're rendering 93 million triangles. Did I do the math right? Yeah, I think this is accurate. So okay, we are rendering 93 million triangles right now. Clearly, there's a bunch of problems in the sense that we are like utilizing the GPU pretty well, but we are not doing that very efficiently, if that makes sense. As in, you could get the exact same picture on screen, hopefully the exact same picture on screen, without pushing 93 million triangles through the rasterizer. I mean, technically we are culling some of the stuff away with backface culling, except that when we use the old, like, traditional rasterization pipeline, we are not doing that, right? So yeah, so here we are pushing 93 million, here we are pushing slightly fewer, or slightly less, slightly, yeah, who knows if it's fewer or less. So there's several issues, right? So the first issue is there's actually quite a bit of meshes behind us, but we are still rendering everything because we don't have any object culling, right? The second issue is there is quite a few meshes in front of us that are kind of far away, and some of them are really far away. Well, pretty far away. And we could be doing LOD, but we aren't, right? So like, I'm pretty sure that like this kitten, which I think was like 30,000 triangles or something, even this kitten, I don't know if it needs 30,000, but like this kitten definitely doesn't need 30,000. I think there's this probably monster or something, and there's probably somebody up close, but like this guy could use like, I don't know, 100 triangles, right? So that is a problem, but that problem we will not get to solving today. Today we'll just want to set up the basic sort of code for culling meshes and see if doing frustum culling will help us here. At which point measuring the number of triangles per second that we are pushing will become even harder, but we will ignore this for now. So the way this will work is this. The way this will work is I kind of need these guys in the draw call structure as well. Yeah. So let's set this now. It's maybe not obvious why we will need them, but just trust me, we will. And like, it would be at some point possible to move this. There's like 20 bytes here that are describing the mesh. We could just store one 4-byte index into some other buffer, and that might be better, because when we do LOD, initially we'll just do it in some stupid way, but like ideally we'll store something like float like LOD distances here, like, I don't know, like let's say like 4 of them, right? And that's 16 more bytes, and that gets silly. So at some point this will have to move out of this struct, but that requires an extra buffer, which we could do, but do we really want to do that? You know, not now. But yeah, at some point definitely. I mean, we could do this now. Should we do this now? You know what, whatever, it doesn't really matter. Let's just set this for now. Index offset. Things should work. Okay, and let me switch to debug actually, because we'll be using some more Vulkan stuff right now. So I want validation layers to tell me when I'm doing things wrong. Okay. So what I want to do first is we have this command data right now that we are generating, and I want to move that to a separate buffer and compute that buffer from the array of mesh draw structures on the GPU. And initially it'll just be sort of a copy step. I'll just take, you know, whatever date is here and just copy it here, which is why I added this. But then we will want to add culling to this thing. So let's do that. And I guess for now I'll use the same sort of like union thingy where I just fill the command data with 7 integers instead of like 5, so that it's immediately useful for both pipelines to not have to worry about like having 2 shaders and whatnot. But yeah, so for now, let us just say this. Let's make a struct on the shader side that's actually a more truthful representation of this command data. Let's call it mesh draw command or something. Right, so, and just mirror the C structs onto the Vulkan side. So there's that, there's that. I don't know why it's assigned integer. I don't want it to be assigned integer. And this stuff, oops. Okay, so now I wanna move this out of here into a separate buffer and compute this buffer on the GPU. So let's first just move the buffers around. And let's make a parallel struct here. And that can just be that. Okay. Then let's see, when we have this draw structure, yeah. Oh, actually, you know what? Maybe let's just try to compute shader and, you know, hope we get it right. Let's just, yeah, I don't want to be doing intermediate steps here, because I want to get this done today. And we have time, but at some point our time will run out. So I want to add a compute shader that will generate these commands and do culling, right? I don't know what to call this. Let's call this draw command or something. I don't know. Draw CMD. So it will be compute shader. So it'll just have a main function and we'll have to add support for compute shaders to our code because we haven't really used compute shaders yet. So, but for now, let's just sort of sketch out the how we code. Oh, this has broken new lines. What happens? What happened with new lines? I will need this for culling. Yeah, but I also need the number of things. So maybe for now let's remove that and let's just add. So we'll want a read-only buffer for draw as our input, and we'll want a write-only buffer as it happens. Oops. Of commands as our output. Let's call it draw commands, and then mesh draw commands, right? And then here it's just a compute shader, so it's like kind of boring at this point. After the stuff that we have done on the stream, compute shaders are not interesting. So let's just say yes, there's the thread index, there's the group index, and then there is the draw call index, which is group index times 32, let's say, and we have to do this again. And I don't know that 32 is the right number. In task shaders and mesh shaders, I think the only size that you can use right now is 32, but in compute shaders you can do whatever. And I guess for this one there's technically GL local invocation index, I think. But for now, let's just do that. That's fine. And then what we'll just do is we'll have the same code that we had on the C++ side, more or less. But I guess we'll have to carefully fill actually every single variable, not just the ones that we care about. But it'll be roughly the same code, right? Where we just go and fill this data. And once again, there's some hand waviness about the sort of commands that are, like if we are drawing one mesh, we'll still run this thing 32 times, and there's some hand waviness around why this might be okay. Let's just say that it might be okay. Alright, so yes, we need to fill all of that now. This is boring. So instance count is 1. First index is index offset. Vertex offset. First instance. And then first task, and then task count. Interesting. When we start doing culling for real, there will be a small complication. There will be a small complication. But for now, we will do this in a sloppy way, and then it will cost us performance, and then we'll recover some performance at some point later. But we super don't need to do it now. All right, so yeah. Let's just do the same. So meshlet count plus 31 over 32. First task. And this is basically it. So we just have a compute shader that copies data from the draw call to the draw commands. But the idea is here we can add frustum culling, right? Or whatever other culling we want to do. We can sort of add it. Which I will explain in a second. So now we have to compile this compute shader and run this compute shader, right? And this compute shader will take the buffer with the draw, wherever it is, whatever we call this, db, I think. Was there a buffer called db? Yeah, this guy. But then we'll need another buffer that the compute shader actually copies data to, right? That we'll use as the draw command buffer, right? And that we will slightly reshuffle things. We'll remove things that we won't need. Yeah. And now we just need to run this compute shader before we start our render pass. Oh, and then we will do. Right, hold on. Let me just fix this code. Right, so okay. All right, yeah. So now let's compile the compute shader and run the compute shader, and in general, try to get things working. Now let's fix the errors in our we need to include stuff, and I guess we'll need a bunch of this. At some point I should move this to a separate include file. let's see. What is this for? Oh, this is for like draw ID. We don't need that. We might need ballot, but for now let's just remove this, and let's remove this. Like, this is the standard set of... I don't even know if we need 16-bit storage because we are compiling for Vulkan 1.1, but I think we might. Alright. And I guess in this shader we don't really use it. Oh yeah, but okay, never mind. Okay, yeah, that is good. So now we compiled our compute shader, and it should be here, right? So now we need to load it. We have never loaded the compute shader, but maybe it'll work. We have written code that may work for compute shaders, but we don't know that up until we actually try. So draw CMD compute shader, draw CMD comp. And then we need to create a program and a pipeline. And something I want to do that I wanted to do before is that for compute programs, it might make sense to just create the pipeline like right ahead. Like when we create, the program is like a set of shaders and we are creating some template stuff, but I think it might make sense to just say, hey, for a compute pipeline, for a compute program, there's no like state that you need. So to simplify our code, maybe we should just create it there. I don't know if you don't need state or if you... Oh, I guess you might need specialization constants or something like this. I don't really anticipate using that stuff. But okay, yeah, for now, let's just do the same thing that we were doing before so that we don't, like... So that we follow the exact same path. So, compute shader, draw CMD, compute shader. Don't really use push constants. Is there like a... oh, there's no... Yeah, I guess let's just do 0. And then we need pipelines. Okay, let's add a function for now. Draw CMD pipeline, create compute pipeline. The function doesn't exist yet. Device, pipeline cache, and right, and I guess this again. Yeah, this is kind of like really redundant, and we don't need more than one because it's only always, yeah, okay. Oh, but then we need, right, this guy. Okay, so let's just add this function. Device, pipeline cache, shader, and then vk pipeline layout. The process should be dramatically simpler, so this function for the graphics pipeline is like 70 lines long or whatever, and we were really, what do you call this? Like, damn it. Basically, we try to use as few lines as possible. For compute pipelines, it's easier, so there's a create compute pipelines device call. It has the usual, you know, create info and stuff, and it returns a pipeline, and you return it. Oops, vk pipeline, and there's a vk check that you need, and then there's vk pipeline create vk compute pipeline create info. Alright, and this should have very few bits of state, like really not interesting. So there's base pipelines, which I don't even know why that's a thing for compute. That's kind of interesting. Maybe if you want different layouts, but why would you want that? So basically this, we'll just ignore this. This is like not useful. And then we'll just need to fill these three things. And so layout. Passing here, I don't think we need that at all. Yeah, so no need for that. Yeah, so outside of specialization constants, which we don't use really, there's like nothing interesting here. So we could have just created this, like when we create the program, but I guess that's fine. Let's just steal this code. We are already doing this somewhere here, right? So let's just steal that code. Right. And I guess we can assert that shader stage is that. Wait, is this the right type of stage? Is this the right enum? It's not the right enum. This is the right enum. Oh, and we don't parse this out of this PRV right now, which is great. Oh yes, I wasn't sure which PRV execution model this is. So we'll have some assertions now, and this is good because we can fix them easily. Yep. Let's see. GL compute. Okay. So apparently you have to use there is like GL compute and kernel, but I guess kernel is actually CL kernel, like OpenCL kernel, and this is what we need to be using. So let's add that here. Alright, so that's good. Now, we've created the program, we've created the pipeline, we'll have to destroy this stuff later. But the more important thing is that now we have to run the compute shader before we do draw calls. Like here or something. So the way we run compute shaders in Vulkan is with cmd dispatch, and you specify the number of groups that you want to run. So like we have, it's the same computation as we did with meshlets. So we have some number of draws, and we have to round it up to the 32 byte, 32 like count boundary. There will be some things that are sort of not initialized, but we might be okay for now because our buffer is pretty large anyway. And then of course you have to bind the pipeline. So let's do that. Wait, wiki pipeline bind point compute, and this will be draw cmd pipeline, and we have to bind resources, right? We can use the same thing that we were using for the draw call. Let's just do this like this. So we need to pass the draw call buffer as an input and the draw command buffer as an output. And in theory, everything else should happen magically, you know, like in theory we don't have to do anything else. But I don't know that this is true. So that... Okay, and the only other thing is we kind of need a couple of pipeline barriers. But as usual, let's start without them and see what happens. Okay. We clearly haven't broken everything completely, but we clearly aren't doing this right. Okay, let's see. So yeah, so let me first destroy things that we need to be destroying. Basically that. Oh, and we created another buffer, right? Oops. What is going on? Do we have... Oh, shader model, right. Wait, no, hold on. It should be destroyed here. Oh, right, no, never mind. Right, okay. Never mind. Yes. This is getting a bit repetitive, so we might wanna abstract some shader stuff further. Okay, so we're running without validation issues now, but we are clearly not rendering like most of the meshes. Right, so let's see why that might be. Let's see why that might be. Have I mentioned that we don't have a working debugger? Well, actually that's not true. RenderDoc will work if we pretend that we don't support mesh. Oh no, there was a problem with RenderDoc as well. I think the nightly RenderDoc build worked. Okay, I wonder if we'll have to use a debugger on stream. So we are missing a couple of pipeline barriers, but I don't know that they would be crucial. We clearly aren't getting validation errors, but this means nothing for pipeline barriers. I mean, maybe this is actually crucial. It might be. But I would expect different sort of bugs to happen in this case. But okay, since we need to add the barriers anyway, let's just add the barriers and then we shall see. Let's steal them from somewhere. There is a question on chat. Is Vulkan worth learning? I have known and used the you know, it depends on what your goals are in life. If you want to make games, then you don't really need to learn Vulkan, because like games are such a varied field, right? There's so many things that you could learn. Why learn Vulkan over any other thing is not super clear. If you want to be a graphics programmer, I would recommend learning Vulkan. Even if you don't use Vulkan, it sort of expands your understanding as a graphics programmer. So from that standpoint, right, it's clearly potentially very valuable. But yeah, otherwise, you know, it's a complex API. Alright, yeah, so we need barriers. Basically, the most important thing that we need is we need a barrier after the compute has ended, which is to say, hey, we have ended rendering this this buffer. Sorry, we have ended like running the compute shader that fills the buffer with draw commands. Let's wait for that compute shader to finish before starting to use that buffer. So, and it would be ideally nice to merge this barrier into like this thing or something, but for now we'll not do that. So let's just call this call like cmd and barrier. So we need to say that we have this DCB, which is the draw command buffer, and we were writing to this from the shader stage, but I don't remember what this is. Wait, access shader right. So we were writing to this buffer from a shader stage, and now we will be using this as an indirect buffer, right? And then pipeline barrier something. So we were writing to this from a compute stage. Compute barriers are much easier to write, because there's like one stage basically here. So yeah, this is nice. I'm not sure what the other stage should be. Let's see. Draw indirect, yeah. I don't know if I need this. I definitely need this for the like other stuff, but for buffer barriers I don't think I need that. And then some of these zeros. Yeah, so this guy is the buffer memory barrier count. So that's the most important barrier. We might want to add a barrier at the front, but it's not that important. But yeah, so the issue is we're not really... Oh, and like some of the meshes are sort of... Yeah. So we are super not doing things correctly, but I'm not sure why. So that will take a bit of time to debug. Because at this point I have no... wait, let's check the other thing. Okay. So the mesh shading pipeline sort of draws something. The non-mesh shading pipeline draws nothing. Okay. That is gonna be fun. So we are clearly like feeling maybe something with data, sort of, possibly. We are possibly feeling something with data, but we are probably not doing this correctly. And I do not know why that happens yet. So let's look at this code first. This code looks correct to me. What could happen is that the data layout could be different between the C++ code as usual and the shader code. I'm not expecting this to happen really, because this guy has like 7 integers, right? And the other guy should have as well 7 integers. And I think we have removed... Yeah, we've cleaned up this... Oh, did we... No, this should be 16-byte aligned as well, so this is all good. So this is 5 integers, this is 2, so that's 7. So that is all good. I don't see any problems here. Let's look at the buffer initialization stuff. So that is correct as far as I can tell. So then we copy to that thing and then we use that thing. Okay. Okay. Never mind. We forgot to wait. I thought it's called mesh draw command. Why is IntelliSense not? Yeah, okay, IntelliSense. Yeah, okay. When you do draw indirect, you have to tell it the stride of your structures, and we just forgot to change this when we moved the struct out. Okay, so maybe this code works now. Okay, so the mesh shading path sort of looks like it works. The non-mesh shading path does not look like it works. Which is interesting. Which is very interesting. Because why would it not work, right? It's sort of nice because we cannot debug the other thing with the debugger, but we can debug this thing with the debugger. But it's also like, what is... Oh, wow. And our GPU time is really, really small. What? Why? What? Huh. This is awkward. Damn it. I want to get to culling and I need to debug this, but I don't want to spend a lot of time debugging this because I really want to do really basic frustum culling, but we need to debug this, right? Like, this clearly does not work. Damn it. Okay. DCB, mesh draw command, indirect, draw size, draw command. This is all... Now it's all good. Alright, let's stare at this. Oh, wait, how are we... Hold on. How are we not passing this data to the draw buffer? Oh, because it's just 128 megs. Where is this draw command buffer? Okay, yeah, that's kind of just 128 megs and we don't care. Okay. Indirect and storage. Something's broken. Oh, did I forget to? Of course I forgot to. Okay, alright, yes. Every time this happens. Okay, alright. I am now much happier because I know what the bug is. The bug is we forgot to pass the data that is actually required to generate these commands for the non-mesh shading path. Alright, phew, okay, cool. Alright, so let's submit this code because I don't want to break this. This again more carefully. Okay, cool. Yeah, we might want to refactor the... Oh, this is the new line. Interesting. We might want to refactor the compute shader support later a bit. Like, our shader stuff is getting slightly unwieldy as we add more and more shaders. We need like 5-6 lines of C++ code to add a shader, which for rasterization, you know, there's like complex work that you need to do, but for compute it's kind of silly, so we should really clean that up. But yeah, okay. So day 11, use compute shader to generate draw commands. Now this is just a straight copy without any culling. We've split the draw command buffer from the draw buffer. Alright, so now let us just quickly, in a bit of time that we have left, implement basic frustum culling, and things will be beautiful. I mean, fast. They will not be more beautiful than they already are, but they will be fast. Okay. So basically the thing that we'll do for now is not very efficient, but we will just set this guy to 0, and when we do so, I'm expecting that well, okay, in the traditional pipeline we'll set this guy to 0, in the meshlet pipeline we'll have to set this guy to 0. Alright, and so this is not super efficient necessarily because, well, it runs pretty fast. Like in theory this is not super efficient because the GPU still takes time to go through these draw calls, but actually on a second thought I was thinking that we may have to do like more complex stuff with like compact buffer compacting and stuff like that. But like thinking about this, it's not that many draw calls. I mean, maybe if there's like way more draw calls, it's like way worse. So let's like hypothetically, right, what if every single draw call was called away? Right now we only have 3,000 of them, so that's not a lot. Let's say we have 300,000, and I don't know if things will work, but I'm hoping they will. Right, yeah. So when you get into the hundreds of thousands of total meshes in the scene, then you see we are spending 3 milliseconds doing not much, right? We are basically, I mean, we have to write this large buffer, relatively speaking, but it shouldn't take that much time. So what really happens is then when we pass this buffer to the GPU, it has to chug through 300,000 draws, right? And every draw doesn't generate work, but the GPU command processor still has to go through that. So that's not very efficient, but we will pay a small price right now of this inefficiency, and then we'll have to correct this later, and later might be tomorrow, or later might not be tomorrow. Actually, maybe tomorrow. Yeah, it would be interesting if tomorrow we basically did LOD support and this like optimization so that we can draw like a lot of meshes with relatively good performance. But for now, we will just basically zero things out, right? No mesh shader. Okay. So to do that, we need to do culling. To do culling, we need two things. We need some data to do culling with, which is basically the planes for the frustum, and we need something to cull, which means we need bounds for the mesh, which for now we will just store a bounding sphere and figure it out later, you know, like that. And then we'll do the same thing. Oh, I guess we are starting to use GLM now, so we should do GLM like 3. Again, not the most efficient data-wise. Like ideally, we would split all of that out into separate struct. Won't do this for now. Maybe a good idea to do either tomorrow, maybe not tomorrow, but at some point. Or if we get to it tomorrow, we can do it tomorrow. So I want to add this to the mesh as well. And this will be sort of like local space center, like we'll still have to transform this by this stuff. But this should not be hard. So now we have to compute this and then copy this. Let me add the copy step first because I forgot it last time, and then we spent like 10 minutes chasing the bug. That was just one line. So let's do that. Then we have to compute this. For now, there's some code in like Mesh Optimizer that can compute a more or less optimal bounding sphere, and it's pretty fast, but it doesn't have an interface. Oh, actually, wait, it sort of does have an interface. Oh, does it? No, it limits the index. Okay, never mind. Like maybe there is a function here, which is a nice function that computes a bounding sphere. And maybe I should expose this at some point. But for now, we'll do something stupid. We'll just say, hey, let's just compute center. Start with 0, right? And then we'll go through all vertices. We'll add the position, which is floats. Okay. And then we'll not normalize, but like divide this by the vertex count. So this will give us the approximate center of the bounding sphere. It's not a very good approximation, but for the time being it's okay. Bounding sphere is not necessarily the best way to call meshes, but for now it will be simpler and less data, and then we'll figure things out later. So then we need a reuse, and then we just go through all vertices again, and then we say that reduce maximum of radius, and then GLM distance, I think it's called, yeah, center and GLM 3. Man, it's so nice to have a math library. So when I write code for Mesh Optimizer, there's like a critical rule in Mesh Optimizer code. There is zero dependencies on anything other than the C standard library, not even C++ standard library. But C standard library is fine. It's hard to do things without that. C++ standard library, no. So this results in code that is not very hard to write, but it's slightly painful. It's like you look at these things and there's all of these computations with floating points, and with a math library you can do that in like 5 lines of code. So it's nice to have a math library. If you the trade-offs are different. Like for Mesh Optimizer, no dependencies is much more valuable than easier to write code, but for our demo application, clearly it's better if it's easier to write code. So that's good. Alright, so we have computed hopefully the bounding sphere maximum. This looks correct to me. Now we need to call this. So now it will already be automatically sort of passed to the shader because we've changed all of the structs to have this data, and now we need to just use that in our compute shader to figure out, hey, is this thing visible or not? So we'll have to compute bool visible. Let's just call it true for now, and then here we'll say if it's visible it's 1, otherwise it's 0, and here we'll say if it's visible it's meshlet count, otherwise it's 0, right? It's visible. Pretty simple. And so here we just need a function that can tell us is the sphere visible from the point of view of the frustum. The canonical way to do this is you compute 6 plane equations. Our far plane is infinite, so I guess we only need 5. But the fact that our far plane is infinite is not optimal. Like, it's fine for depth distribution, but it's sort of weird because it would be nicer if we could actually have a max draw distance, right? But we'll figure it out at some point later. For now, we'll just say there's 6 planes. And we'll push them in, push constant. We'll like use a push constant to communicate them to the shader. I think it was uniform block. I already forgot how to use push constants after the first time that we did that. Yeah, uniform block. Hey, I did not forget. Okay. And we basically just need frustum planes, 6 of them, right? And then for each plane, we will say that if the sphere is completely outside of a plane, is there this guy, I guess? Maybe I shouldn't use bools. Maybe I should use like ints, and then I can actually use bitwise operators. I wonder if that's true. So what we want to do first is we want to get the sphere and transform it to world space. So the center of the sphere is just the draws di center plus times draws di scale, and then plus, I should call this maybe mesh center. It's fine for now. Once we refactor the code, like you probably want to fetch this from a separate buffer with just mesh data, so that you can have like hundreds of thousands of draw calls at less memory cost and less bandwidth cost. But I guess good enough for now. So yeah, this is just transforming the sphere to the world space. And then this guy will be radius times scale, right? We don't support non-uniform scale, and we don't support arbitrary transforms in general. We support rotation and uniform scale, which makes it easier for us to transform spheres, right? Because like when you transform a sphere using uniform scale, you get a sphere. When you transfer a sphere using non-uniform scale, you get like an ellipsoid or something, I don't know. All right, so, and then we basically just need, we can like even add a loop. It doesn't matter. Well, oh, I wonder if there's unroll qualifiers now in GLSL. I think there are. Okay, so let's just do this for now. So basically, we need to say that the plane equation defines like the sort of how far the point is from the plane and which side it's on. And I never know what signs to use anywhere, but let's just say that if it's like less than, for example, I don't know what the right thing to do is yet, then minus radius, or maybe greater than radius. Well, right. Yeah, or maybe basically the deal is this. So there's a frustum, right? Does this work? Aha, it works. It's just slow for some reason today. So there's a frustum, and there's a sphere, and there's a frustum plane, right? And there's like a sphere, like let's say here, and there's the center of the sphere, and we measure the distance between the center of the sphere and the frustum plane, right? So if this distance is radius, and let's say the like plane equation is defined so that there is a positive half space outside of the frustum. In which case, if the distance is radius or more, then the sphere is outside. But if it's less than radius, so like in this case it's like radius over 2 or something like this, right? Then it might be inside. So we need to say that if any plane has a distance that's greater than radius, then Wait, right, if any plane has a distance that's greater than radius, then the thing is invisible. So we have to add the less than radius equations for all planes, and if any one of them will be false, which means greater than radius or equal, then we know it's outside. So that should be correct, I think. And then if the far plane is infinite, and then maybe if it's all zeros, then this thing will be 0 less than radius, which is true. So it's gonna be fine. So this might be correct. Now we need to pass this data to the compute shader. Thankfully, we have implemented support for push constants, which should just work. So we should be able to just say here, we need, for now, let's just say we need like 6 like vec4s, right? So how we're gonna create these frustum planes? This is the part where I don't want to derive this math. I just want to sort of wing it. Like, it's faster. Like in some parts of computer graphics, it's very valuable to derive things very precisely, like every time. But occasionally you have derived it once, and then you could rederive it every time you want to use that, or you could just store the piece of knowledge somewhere inside, like an article or something. But what you can also do is you sort of remember how you have derived it and how the form of the equation looks, but you aren't really sure about some specifics, like the column or row ordering or the signs or something. And in many cases, it's generally faster, and it's not like terribly bad to just brute force this. Like, okay, so the way this works is there is the frustum planes. And frustum planes, frustum equations can be derived from a projection matrix by adding either rows or columns, and this is what I don't really remember because I don't even know what I'm using, column or row major, but it doesn't matter, of the projection matrix, which means we need the projection matrix, by the way, and we need it earlier. So let's move this here. GLM@4, is it? No, don't remove the name. Okay, hold on. What was this global thing again? And this could be a view projection matrix, but right now our view matrix is identity. So yeah, like the way this works is, projection. And again, we may get this wrong because of column issue or row column issues, but there is equations that go like this. So there is an equation that say that essentially x over w should be, maybe I can get it right without deriving that and without thinking too much about that. So our plane goes, I want to have stuff that is outside be positive. So I want the equation, but the plane sort of tests are, say, x over w is less than -1, because the clip space is between -1 and 1 in x and y, right? But this is equivalent to x is less than -w, which is equivalent to x plus w is less than 0, right? So then if I just add sort of the rows or columns or something corresponding to x and w, which is 0 and 3, so in this case it's add, right? Then if x is large, which is this guy, then the thing will be positive. So I guess maybe this is correct. We'll see. So then the other thing is basically x minus w, I think, because it should be x over w is greater than 1, which is x is greater than w, which is x minus w is greater than 0. And the sign here is different. So that actually might be wrong now, because I think maybe I should do it like this. Maybe. All right. Maybe this is correct. Maybe this is, maybe this is not correct. But it might be close enough. So the z equations are slightly weird. The z should be the near plane. We don't even have the far plane, honestly. But if we had a far plane, and we have an inverse z. Oh, I never done with an inverse z. Inverse z is interesting. So with an inverse z, your near plane is at z equals w, and your far plane is at, which should be infinite, but still, is at z equals 0. So this, and we want, like, for our outside test, z greater than w, so z minus w greater than 0. I will leave a note here that we have a reverse z, and this should canonically, I guess, be z is like less than 0, but we actually have an infinite reverse z infinite far plane. So this this should be 2, and this should be minus, but this should probably be just 2. But the thing is, this guy is 0, like maybe this is this, but this guy is 0, so it's probably, so like since the far plane is infinite, probably none of this actually makes sense for the last frustum plane. But okay, so like the code looks roughly like this. I'm sure there's bugs here, but it's faster to, as I said, first just write this code and see if it maybe works, or maybe like tweak it so that it works, and then we can derive this more carefully if we need to. But I don't think we need to do this. If you want like a more, I'm obviously not explaining why things are like that. Wait, it's not CS, it's program. But there's plenty of articles on frustum culling, so I don't wanna spend my time doing that. I just want this code to work. Let's do a sanity check. Also, let's fix something. So it doesn't want to compile my beautiful integer code somewhere. In line 36. Oh, okay, that's fine. And in line 38. Okay. Okay. So it really wants this to be a boolean, basically. Okay, you know what? If it wants it to be a boolean, let it have a boolean. Oh, and it doesn't. Okay. Alright, happy now. So now I want to just debug the frustum planes and, be done with that. So yeah, as I said, the fifth frustum, let's just do it like that. Oh wow, the GLM is not very friendly for debugging, because it shows you 12 floats for every vec4, even though they're the same, because they support like .rgba and .stpq and .xyzw. So yeah, interesting. Far plane, maybe I actually flipped it in my head. I expected this thing to be, but maybe I need to be using columns, not rows. It could always be a thing. I don't even know what this subscript operator does in GLM. I don't expect this to, wait. How curious. I think it's saying that our beautiful push constant stuff does not work. How is that possible? Let's see. The push concentration in the layout doesn't contain the stage flags 0x20. Oh, That's too much for push constants, isn't it? Isn't it? Well, I guess not on this driver. Interesting. No, but wait. We are not using... We're using 96 bytes of push constant data, which is perfectly within limits. What does it want from us? Right? That is odd. Hold on. Okay. So this happens when we do push constants. Push constant stages is the 0x20, which should be the compute stage, unless our code just doesn't work really. Yeah, so we are saying, hey, our compute shader, like, did we... No, the layout is correct. Right? Oh, times 16. Oh, oops. Okay, never mind. Okay, yeah, so our frustum culling clearly doesn't work, right? But, you know, I'm sure we have messed up the math somewhere. So let's replace this side with of frustum. So I'm really unsure about this plane. This plane feels weird to me. It should not be 0, 0, minus 1. And let's just remove all planes. Let's remove these ones. I'm slightly more sure in the other ones. Okay. Do I need to derive this? I really don't want to. I need to think about the signs here. So I feel like the signs might be flipped. Maybe. So let's think about this again. When we have the frustum plane that... So what I'm saying is, I think my check, let me double check this, but I think my check says that, yeah, the positive half space is outside of the frustum. Yes. So the positive half space is outside of the frustum. So for example, let's just get the planes right, and we don't have a way to visualize our culling or even know that it culls anything. But let's just do this one plane at a time. Well, so in this case we should be good because, yeah, because all planes are sort of dummy planes, they don't cull anything. So I'm expecting that even the first plane is not really correct. And there could be two reasons for this. Right, yeah. So we culled something around the plane, but the plane is not even right. And also the... yeah, so there's like many problems here. So I think the first problem is that we probably are using like rows instead of columns or something. So let's check this theory. And then the second problem might be that the signs here are broken. So now the second problem might be that the signs are broken. So I guess I can just do, or I can flip the meaning of my planes in this shader and say that this should be a little bit greater than minus radius, in which case the negative half space is outside of the frustum. Okay, probably that was it. So let's try to... Oh, and this might explain the weird far plane. Yeah, so my guess is that, again, I never know whether like the matrix library that I'm using at this point in time, which right now happens to be GLM, has like rows or columns or what. I don't know what subscript operator does, but so this seems... Oh, and we are way faster. So yeah, okay, I think this is like working. And now again, our triangle count per second metric is just not like, it's saying we are rendering 100 billion triangles per second. Well, we aren't really rendering 100 billion triangles per second because we are culling a lot of this stuff away. But okay, so this is encouraging. So I think all of these equations might have been correct, except for maybe the sign here is broken, but this guy should be 0 no matter what. So let me look at that. No, not this. Oh, this should be projection T. Wait, hold on. Frustum. Well, it's not quite 0. Which is slightly surprising. Oh, this is not Z, this is... No, this is Z. Interesting. Again, I haven't really done this with the infinite projection matrix. I don't know if this should work. But I sort of expected for Z to be 0, the point should be basically at infinity. This is what we are clearing our depth buffer to, right? So this plane equation says that we are oh no, okay, this is correct, maybe this is correct. Yeah, because this guy is 0, so this is not really a valid plane equation in that sense, but it still defines a half space in a weird way. Yeah. So for now, I'll just wanna do this, like, yeah, because we have an infinite far plane. Now, ideally, this should be computed in a special way for reverse Z matrix, so that we actually get culling. Beyond a certain boundary, right? So like here we'll want to say that we have max draw distance, which is like 100 or whatever, or 1,000 or whatever our units are, right? Or like 10,000, doesn't matter, and then we will call with that. But okay, so for now maybe this works. I want to just double check that all frustum planes in isolation call enough things for us to see performance benefit, because this is what I'm expecting here. Like the near plane should call everything that's behind us. The left plane should call everything that's to the left of us, which also should be like half of the objects or something. So we should have, what should happen is that if we just use one plane, so if you just say visible is this guy, right? For any value of I, we should have meaningful, except for 5, we should have meaningful benefits. So yeah, so 0, 3 milliseconds, so that's like twice as fast. 1, twice as fast. 2, twice as fast. 3, unfortunately these benefits won't accumulate. You can just say that the result is 32 times faster, just because every of the 5 planes calls something useful. Okay, so I feel like this works. Ideally to debug frustum culling, yeah, okay. Ideally to debug frustum culling, we'd implement a thing where you can move the camera, and then you can freeze the camera for culling, and then you can move the camera outside, and then see that your culling works. But we don't have a way to move the camera, so for now, let's just assume this works. Alright, yeah, so when you cull with all planes, we get like 1 millisecond, which is like 6 times faster or something, which is good. Okay, so that is encouraging. It seems like our frustum culling works, with an exception of this plane, which I basically had to disable because I don't really trust this. Oh, it's actually easy to do. It's not that hard. Hold on. Let's do this. So this is not that hard, I think. Let me think about this for a second. And I'm out of tea. Let's just briefly look at chat. So, assuming this thing is correct, which I think it is, here's what we know about the far plane. So the far plane, yeah, this should be super trivial. Okay, so like the there's no far plane in our projection matrix, right? It's just not a thing because we have an infinite, a reverse infinite z projection thingy. Like we have a near plane, the near plane is 0.01, but we don't really have a far plane. So like in theory, every object that we draw, no matter how far it is, it will render. It's just, it might be like 5 pixels on screen, but it will render, right? But it's still valuable for us to say, like, we'll call things beyond a certain distance, and it's trivial to build a plane for that because, or should be trivial to build a plane for that because the W value here is basically the distance to the camera plane. For, like, if you don't know why this is true, you should read about projection matrices and stuff. But this is basically true. Now, it could be the minus distance in the sense that like things that are in the front could be like negative W. But I think the way our camera was constructed is that W in front of the camera should be positive. So, if we wanted to cull things away, and so here we are saying like the plane defines an equation that culls things away once it's like negative or whatever. But what we want to do for the far plane is we just want to say, hey, if W, aka distance to the camera, is greater than some like far, like let's call it draw distance, right? Then let's just not draw this thing, right? Which is equivalent to saying that W should be greater than draw distance, which is equivalent to saying that W minus greater than draw distance should be greater than 0. For us to call the thing away. And again, like, I'm not sure what the signs here will be, but basically this just boils down to, oh, but I can synthesize this value from, I can, oh, wait, hold on. Yeah, okay, it doesn't work like that. I was hopeful. Well, no, wait, it does work like this. Doesn't it work like this? Yeah, you know what, wait, this is stupid. I'm not doing this right. I just want to write code that will not break when we add view matrix. Like right now, the equation is actually like z minus draw distance is greater than 0. So right now, I just need something like 0, 0, 1 minus draw distance, or maybe 0, 0 minus 1 draw distance. I'm not quite sure. Let me see how far our meshes are generated. Wherever this code is, it's here. So it's like between, so it's like 20. So if our draw distance is like 5, let's see. I don't know if we did anything. I definitely didn't do anything. We've been using that. We are. That should not be the case. Yeah. Oh, is it? That makes no sense. Alright, I guess it's not as easy as I thought. This is weird. Shouldn't this work? Because I'm passing world space data, which is the same as view space data, in which case I only care about Z, and if Z is if Z plus, so this says Z plus draw distance is greater than minus radius, and then it's visible. So if Z minus draw distance is greater than minus radius, so this should be draw distance minus Z, so it should be this. I think this should work. I don't understand. If it doesn't, I don't understand this. Maybe one is too close now, but okay, maybe this actually works. And then beyond like 40, we don't really have any meshes. Okay, so maybe this actually works. Okay, yeah, so because we have reverse Z, we can't really compute this from the projection matrix because the projection matrix is infinite, like has infinite far plane, right? So it doesn't have a far plane really. So I guess for now we'll have to settle for that. And then when we add a view matrix, we'll have to transform this plane by the view transform. But that should be easy enough. And that way we actually have a draw distance that we can vary. And now that we are rendering things much faster, let's just add more things. Let's see how far we can push with culling, with basic frustum culling, how many total sort of random meshes in our scene can we have. And I want to expand the bounds a bit so that it's like less cramped. Okay. So this is still 2.5 milliseconds, so not very interesting. And so again, the challenge is we don't know how many triangles we are generating for the G. Oh my god, that was a bit excessive. But hey, it still runs at, 50 FPS. And then it's way slower with the old pipeline, as we have discussed before. Alright. So like it sounds like if you want to really push a lot of geometry for this GPU, you kind of want to use the mesh shading pipeline. So yeah, so the problem is basically these numbers are meaningless now, because it's saying we are pushing 3 billions of triangles per frame. Well, this is not true because we call a lot of them away, right? But what is also true is that, as we saw before, like even if we called everything out, we'll pay a cost of draw call processing, and for 100,000 it must be substantial already, right? We're also running in debug mode, but that probably doesn't matter much because almost all of the work that we do is on GPU. Yeah, so let me cut this by half so that we are running at like 10 milliseconds per frame on my GPU, which is a comfortable number. It doesn't seem too slow. But also there is, oh my god, there's a lot of stuff on screen, right? So yeah, let's see at this draw count, and I don't want to do anything with that today, but let's see at this draw count what would have happened if everything was invisible. Right, we'd still be paying 0.7 milliseconds for, maybe for culling, but more likely we are paying this for the actual draw call submission. And we can measure the time that culling takes separately. In fact, let us do that, because we have this query pool business with 128 queries, but we only use 2 of them. So let us use queries, let us say, like, I think we use 0 and 1 for the frame, so let's use 2 and 3 for the culling. And then when we read out data, let's read 4 queries, and then we can do like call GPU time, right? And this is where I really want a profiler, because this is getting old, but we will not do this now. And I don't think we will do this tomorrow, but at some point we will need a GPU profiler. So let's see, I'm expecting that culling basically takes no time at all, but I don't know that this is the case. Call GPU time. Right, so we are taking like 0.03 milliseconds to use our shader to do culling for however many it was. Like 50,000 draw calls, right? So this means that with 50,000 objects with this GPU, you like don't need, if you do GPU side culling, you don't need like oak trees, or like you need nothing, right? Like even if this value was like 10 times higher, we'd still be running at like less than half a millisecond for culling on the GPU. Of course, if I actually try to increase this draw call count by 10x, then we'll start running really heavily into the triangle count limitation, right? Like we are pushing a lot of triangles right now. Like even though we are culling, we might be culling like 6x or something, but even if we are culling 6x, this means that we are pushing, what is it? It could be that we are pushing right now, yeah, like 200 to 300 million triangles. So obviously, again, right, we don't have to use that many triangles to render this scene if we had LOD. So this is what we'll be doing tomorrow, but today I feel pretty happy with the progress, right? So to recap, we have we've done a bit of code refactoring, but more importantly, we have implemented multiple meshes. So you can clearly see now you cannot render this scene with just instancing with like a single draw call, right? Which we are doing right now. And we are doing completely GPU based culling and submission. So there is a single, almost completely, sort of completely, there's a single dispatch that does frustum culling on all of these meshes, and then outputs data for the rasterizer to use, and then rasterizer in either mesh shading or the non-mesh shading pipeline uses this buffer using drawing direct to render all of this stuff on screen, right? And we are pushing a lot of triangles, but this is because we don't have LODs yet. So tomorrow we'll do LODs, and maybe tomorrow we'll do draw compaction. Because yeah, the other thing that I mentioned was that even if everything was culled away, we'd still be spending like a millisecond here on not rasterizer, like command processor discarding empty draw calls. And tomorrow when we do LOD, I'm expecting that we'll be able to push up the draw call count like 10x or more, which means we'll have to expand the, right now this is a relatively compact area that we are filling with meshes. But anyway, and then we will, I think, start to be hitting the limit of empty draw call commands really hard, at which point we'll have to fix that. But, you know, this is it for today. I think this has been pretty good. I am happy with the results. I'm not happy with this white space. Damn it. I wish there was like a thing, you know, like, so Git is really unhappy about stray white spaces. And random editors don't really care too much about stray white spaces. And some editors, like I think Sublime, have a setting that says, hey, let me like remove all trailing white space from a file when I save it. But then I always feel bad about using this setting, because if you work on a code base that's not in Git, then you just generate like extra white space changes for no reason. So I wish editors were more careful about not adding new white space lines instead. Okay, so I think we are good here. Yeah, so let me commit that, look at chat, I'll answer questions if any, and then we'll call it a day, and then tomorrow LOD, draw compaction, and you know, whatever else we might do. We might need to do camera controls after we do LED and draw compaction to really make sure that our LED works okay, so that we can do dynamic switching, but we aren't going to do this for now. What did we just, oh yeah, like implement frustum culling. We now use frustum culling in compute shader and generate empty draw calls for invisible meshes. This reduces rasterizer workload, but is not very efficient in terms of command processor workload for invisible meshes. But we'll fix this later. Alright. Yeah, Vulkan and D3D12 are a bit verbose, but you'll learn more and understand more. Vulkan is like more verbose than D3D12, but it's also more versatile. The interesting thing, I like Vulkan more in general. D3D12 has some weirdness where Vulkan has a lot of weirdness. D3D12 has some weirdness, but the thing is, Vulkan is an open API that I feel being involved in. And there's a lot of extensions that you can use. Like, we couldn't do the stuff that we are doing this on the stream series with D3D12 because D3D12 does not support mesh shading, right? So we could do like the stuff that we did today with D3D12, but not the other stuff. And also D3D12 inherited a lot of weird, really weird API and idiosyncrasies from D3D11, like all of the buffer craziness and stuff like that. So, and then it requires Windows, it requires Windows 10, you know. Like this stream, we could do this probably on Linux just as easily, assuming the drivers are okay there, right? D3D12 now. And also Vulkan is basically a somewhat deeper API, so if you want to study APIs, studying Vulkan, you should study both, but studying Vulkan may be more productive in terms of understanding how GPUs work. Anyway, alright, so that's it then for today. Thank you, and see you guys tomorrow, same time, same place.